strain transpose, right? So virtual strain transpose becomes this transpose, okay? So meaning that this term becomes okay, something like this. And because these are nodal displacements, right? And these are also nodal virtual displacements. So you can pull this off from the integral, okay? Because those are constant values, okay? They are nodal displacements value. So in the end, you would only have multiplied with u hat, okay? So this is basically this term right here, okay? All right. Now, this is for each element. But what you're trying to do is you want to be able to compute this for all the elements within your structure. So what you do is you compute the summation of all elements, right? So you put a summation of all elements, okay? So if you can compute the internal virtual work for one element, you do this, repeat this for each of the elements, for all elements, and then you find the summation of all of them to obtain the total internal virtual work for your structure. Okay. But in doing so, in computing the total virtual internal virtual work for your structure, if there's a way that you can also match your nodal displacement of each element with the nodal displacement of the structure as well. Okay? Because remember that each element is part of the structure, right? So the nodal displacement of each element should be compatible or should match with the nodal displacement of the structure. So if you can match this with the nodal displacement of the structure as well, and do the same thing for the virtual nodal displacements, okay? So then it means somehow you should be able to write an equation for the total structure or for the entire structure, okay? If you can match this, right? The nodal displacement of the elements and the nodal displacements of the structure, then you should be able to write the set of equations for the entire structure as well, okay? So this set of equations, right, can be written for the total structure in this form, okay? But the details on how you can match this, we'll talk about that in a little bit. But for now, just trying to understand that you can somehow match between the nodal displacement of each element and the nodal displacement of the structure. And based on this matching, then you can somehow write this equation for the entire structure in summation form like this, okay? So the idea is you want to compute this term, right, for each element and somehow based on this matching between nodal displacement of the element and the structure, you want to be able to compute the contribution of each of these elements into the total structure as a whole. Okay, to compute this term right here. Okay. So if you are able to do something like that, then you would end up with this kind of equation on your left-hand side. Okay, and that represents the internal virtual work term. Okay. So again, where did this term come from? It comes from the internal virtual work, right? Because it's a product between virtual strain and stress. Okay, and you compute that for each of the elements first. Right. Now, if you look at the term on the right-hand side, okay, the left-hand side is the internal virtual work term. On the right-hand side, you would have the external virtual work terms, right? And those are the terms that come from the product between virtual displacement and the applied forces, right? Now you have three different types of applied force. First one is the body force, right? So the body force is this term right here. Now the second term is the surface traction, and the third one is the nodal force, right? Okay, so you simply compute the external virtual work for each of these different forces. Now you would see that if you apply the approximation scheme that we used previously for the virtual displacement into this equation right here, then you would end up with something like this. Okay. Again, how do we end up with something like this? Because you have del u hat equals and multiply with I'm sorry, this shouldn't be a hat here. Okay, so del u hat transpose is equals to del u hat f transpose and transpose like this. So you plug this back into the above equation here. So you end up with okay, something like this. All right. Now I pull this off from the integral because again, it's a nodal virtual displacement term. Okay. All right. So you can do the same thing for surface traction and for the point nodal force as well. And if we take into account the initial stress, then you will see that the initial stress that should be on this side. Okay, if you put that on the right hand side as well, you would get this term right here. Okay, so this plus sign here, when you switch side, then you would get a minus sign. All right. So if you have the initial strain term, then the initial strain term would be included here. So you can also put your initial strain on the other side as well. Okay. Now, based on this set of equation, then you will see that if you cancel out this and this, right, you would have this matrix multiplied with u hats and equals this all these terms right here, which can be simply written as this equation. So this is basically your matrix K. Okay, this is u hat, and all this is your R. So this is written in the form that we are used to, right? This form of equation is called the stiffness equation that we normally use to solve a structural analysis problem. Okay. But in structural analysis problem, you normally construct this stiffness matrix, right? Directly based on the stiffness matrix that you compute directly for each of the elements. But now you can see that it essentially comes from the virtual work equation, right? This K matrix. It's this part right here, which represents the internal virtual work term, okay? So you can also construct this stiffness matrix as well, because it's basically how you compute the internal virtual work for each element, okay? So you can basically compute this for each element, and then somehow you can combine them together to represent the whole structure, right? So you can obtain another matrix for the entire structure, okay, or this matrix. So you can write your equation in the stiffness equation form, which you are already used to, okay? Now the problem here is that in order to solve this kind of equation, then you need to be able to write this vector or matrix on the right hand side in corresponding components with the nodal displacements, right? Meaning that you need to also be able to write your load components of this vector on the right hand side at the nodal or as the nodal quantities as well, okay? So it means that when you try to compute this, you need to also be able to write this as components at the nodes. Okay. All right. And we'll talk about this concept a little later on. Okay. But for nodal force, you can write that without any problem, because the nodal force is readily available in nodal quantities. Okay. All right. Okay, so we can see that based on the alternative form of equilibrium equation, we start out with the virtual work equation, but in the end, we end up with the stiffness equation. So if somebody asks you what the stiffness equation is, then you can answer from based on our derivation here that the stiffness equation basically tells you the equilibrium equation, right? Okay, and this equilibrium equation comes from the virtual work equation. Okay, so we can use the finite element approximation concept to write the virtual work equation or the alternative form of equilibrium equation, and we can solve our system of equation in the same form of the stiffness equation that you have been using for the structural analysis problem. Okay. All right. So to summarize all the metrics involved, then you see that you have this stiffness matrix of a structure, which needs to be obtained. But in order to obtain that, first you need to be able to compute this part for each element first, which we are going to call the element stiffness matrix. So from the element stiffness matrix, you can somehow assemble them to get the structural stiffness matrix. Okay, and for the load vector part, you can have different load components. The first one comes from the body force. Okay. The second one comes from the surface traction. And the third one, this is the initial stress part. Also, if you have the initial strain part, you can also write it as another load vector as well. Okay. And the last one is the point loads or the nodal force part. Okay. Now, of all these load vectors, you see that only the last one is readily available in nodal quantities, right? But the remaining are not. So it means that in order to be able to use this form of equation to solve for your problem, you need to be able to somehow write all these load vectors in corresponding forms with the nodal quantities. Or you should be able to write these load vectors as components at the degree of freedom at the nodes. Okay. And how we can do that would be discussed later on. All right. But for now, question remains on how we can write this at the degree of freedom, right? Okay. Now we are going to try to apply this concept to an example problem. Okay. So we're going to start by looking at a bar model, but one-dimensional structure. Okay. All right. So in this structure, we have 7 nodes. Okay. So 7 nodes and 6 elements interconnected to each other like this. Right. So because it's a one-dimensional element, so at each node you would only have 1 degree of freedom to characterize the displacement and the force that acts at the nodes. Okay. So we call this displacement and force at the nodes by using these symbols right here. Okay. Now we are going to start by using the finite element approximation scheme, okay, to approximate the displacement field. Right? So it means that, for example, for element 1, I want to approximate the displacement within element 1 by using the nodal displacement here and here. Okay. Okay. So in a generalized form, okay, for an element M with a starting node called I like this and the ending node called J like this, I would want to approximate UM from UHI and UHJ. Okay. So I would have two displacement interpolation functions, Ni and Nj. Now, in this case, Ni is expressed by using this equation and Nj is expressed by using this equation right here. If you look at these two expressions for Ni and Nj, then you would see certain quantities or certain characteristics for these displacement interpolation functions. So what are the quantities or the properties that you can observe? The first one is that you can see that if you look at the value of Ni is equal to 1 at node I, right? And equal to 0 at node J. Why, if you look at Nj, you will see that Nj is equal to 1 at node J and equal to 0 at node I. Okay. The question is, why is this so important? Can my Ni and Nj functions or can my displacement interpolation functions look different from this? Can it be different from this? Okay, let me ask our friends here then. Natachai, are you there?
Yes, I am.
Okay, Krab, Natachai, do you think that our displacement interpolation function can look different from this?
It may be not linear function. It can
ตอบเป็นภาษาไทยก็ได้ครับ
จริงๆพอมันเป็นสองโหนดแล้วครับมันเป็นเส้นตรงได้แต่ว่าถ้าจะเป็นมากกว่าลีเนียร์ฟังก์ชันแบบเนี้ยมันอาจจะต้องเป็นฟังก์ชันที่ดีกรีมากขึ้นครับ
Okay. All right. So Natachai was talking about it has to be a linear function, but for example, can I switch this to Nj and switch this to Ni? Would that be possible? Suppose I have linear functions for both of them, but can I change this place? Like, can I call x over L as Ni? And if so, what would happen?ได้ไหมครับนัทชัย
ไม่น่าได้ครับ
Why not? Problem is why not? Why Ni has to be 1 at node I and 0 at node J? it comes directly from this equation, right? Okay, it comes directly from this equation because of the way you are approximating them like this. So when you substitute the coordinates of node I into this equation, okay, you substitute xi, so you have I, meaning you substitute xi, right? So if you substitute xi, this become what? Xi, this become x hat I, okay? So in order for this equation to hold true, then this should be comes 1, right? So it multiply with this to get this, okay? And this must be 0. Otherwise, you would end up with this in your equation, right? So if you do not make nj equal to 0, what would happen? You would end up with the remaining term of u hat j in this equation, okay? So it means that the nodal displacement at node I would have contribution from the nodal displacement at node j, right? Which would violate this approximation. Do you understand what I'm saying? Okay, so in order for this equation or for our approximation to hold true, you must maintain this kind of properties for your interpolation functions. Otherwise, it would violate the approximation scheme that you're using. All right. So by having this scheme, what would happen then? It means that if you look at node I, then there's nothing from node j, right? No nodal displacement from node j, no contribution whatsoever from the nodal displacement at node j. Only the nodal displacement from node I, right, contributes to the displacement at that node. No contribution from all the other nodes. Okay. All right. Same thing, if you look at node J, you would see that the displacement at node J would comes only from the nodal displacement at node J and no contribution from all the other nodes. Okay. All right. So this is what these properties would tell you or would preserve for you. Okay. So combining this with a linear function that Natachai mentioned previously, then you would end up with this type of equation. Okay, so you can have any other kind of equation if you want this property and you want linear functions. Okay, now back to the question of the linear function. Can I use higher order function for my displacement interpolation function? In this case, can I use higher order? For example, if I want to use a parabolic function, can I do that? Okay, let me ask, who is iPad? Who is iPad? Here? You don't put your name on the screen, just put iPad. Who is iPad? Are you there, iPad? Okay, maybe you don't recognize yourself as iPad. So let me ask no, no, ครับ
เย็นอาจารย์
No, my question was, can I use higher order approximation function for displacement? In this case,
I think we cannot use
and why not? Why not? No?
because it's not a linear function. If we use a higher order function, right?
What and why do we have to use a linear function? My question was, can we use different type of function other than linear function?
I think, in my opinion, I think it can, but it's very difficult to approximate.
It would become very difficult. You think so? Okay. All right. Thank you, Nu. Okay. Now the question on what type of function can be used here not only depends on the difficulty of the function, but essentially on the information that you have, okay, for the function itself. Because suppose you want to use higher order function, right? It means that you want to approximate your displacement function by including higher order terms. Okay, higher order means you have, order that's more than one, right? It's higher order. Okay. Now linear term would include these two terms, right? Okay. So suppose you want to write or approximate your displacement function by using a linear function, you would have two unknowns here, right? A0 and A1. These are unknowns because you do not know what their values would be. But what you need to do is you want to know what they are. What are the values of A0 and A1? So you need to be able to solve for their values. Okay? And how do you solve for their values? What are the information that you have? In this case, you only have information at the nodes, right? Because like we said, we are doing everything based on the nodal quantities. So in this case, you have two nodes. So you have I and you have j as your information. So meaning that you have two pieces of data available. So if you have two pieces of data available, then how many unknowns can you solve for? If you want to try to solve for the unknowns here. For example, if you plug in x hat I here, then you would obtain u hat I, right? This is this, and you would get u hat I equal a0 plus a1 x hat I, something like this. Okay, so this is your first equation. Now for the second equation, you have u hat j, so I plug in x hat j to obtain a0 plus a1 x hat j. This is my second equation. So at most, I have these two equations to solve for the unknown. So how many unknowns can I solve for? You only have two pieces of data available, so you can solve for at most two unknowns, right? So because you can solve for at most two unknowns, you cannot have higher orders in this case. The only way you can include this term, if you want three terms for your approximation, is to add another node onto here, right? Now, if you have three nodes, now you would have ijk. Okay, so now if you have three nodes, you would have three equations available now because you would also know the value you had k. So you have three pieces of data available now. You had I, you had j, and you had k, and you can use three pieces of data to solve for three unknowns. Okay. But now, since you have only two nodes, so at most you can solve for two unknowns. So based on this approximation equation, meaning that you can have only a linear function at most to approximate your displacement. Okay. All right. So seems like when you pick the number of nodes for your elements, you basically limit yourself with the approximation functions available to you. Okay. In this case, you pick a two-node element. So the displacement interpolation function becomes linear functions. Okay. And with these properties as well, it seems that you can only have one set of linear functions for your elements. Okay. So you would end up with this Ni and Nj without any choice for a two-node element. Okay. With the finite element approximation as well. Okay. Keep that in mind. Now, with other types of approximation, you may be able to write different form of equation, but with the finite element approximation, you would end up with this displacement interpolation function. Okay, so with this Ni and Nj, I follow the example, not the example, follow the steps that we have previously. So I can write my n function. Okay, in this case, okay, so starting from UM, okay. So in this case, UM can be approximated by Ni, which is a function of x, multiplied with Nj, also a function of x, and multiplied with U hat I and U hat j. Okay, so this is the approximation function for the displacement field within each element n. Okay, with the starting node I and the ending node j. So based on this, I can compute the strain value, right, based on the displacement field by finding the derivative. Okay, so epsilon in this case would be epsilon xx, okay, by computing del u by del x. So it becomes what? Del ni by del x, del nj by del x, and multiply with u hat I and u hat j. Okay. So basically, this is my displacement interpolation matrix. Okay, and this is my B matrix, right? And again, the B matrix is the what? The matrix that relates between strain and nodal displacement, right? Or the strain displacement matrix. Okay. So with matrix B in hand, if I want to compute the element stiffness matrix, then how can I do that? The element stiffness matrix in this case would be, okay, I follow the procedure that I have previously. So I have this B transpose times C times B, right? Okay. And again, this C matrix essentially is the constitutive relation between stress and strain. And in this case, because I only have one component of stress and one component of strain, so this C is essentially the Young modulus, right? So this is the modulus of elasticity. Okay. So it's a 1-by-1 matrix. Okay. And the B matrix here is a 2-by-1 matrix. Okay. So in this case, the B matrix is 2-by-1. B transpose would becomes I'm sorry, this is not 2-by-1. This is 1-by-2. Because it has only one row. So this is 1-by-2, right? Okay. So this is a 1-by-2 matrix. And this is B transpose becomes a 2-by-1 matrix. So this K matrix would become a 2-by-2 matrix then. Okay. All right. So you can simply use this to obtain a 2-by-2 matrix that looks something like this. Okay. For each of the elements. And once you are able to obtain the element stiffness matrix, then you may want to write the stiffness equation for the entire structure. So in doing so, now you must somehow be able to mesh between the nodal displacements of the elements, right? And the nodal displacements of the structure. Okay. Because as you can see for the structure, for the entire structure, now you have a total of 7 degrees of freedom. Okay, so if you want to write an equation in this form for the entire structure, then this stiffness matrix of the structure would be 7-by-7, right? According to the number of degrees of freedom of the structure. Okay. And this U hat would be the nodal displacements or the 7 components of them. So this would be a 7-by-1 matrix. And also the load vector here would be a 7-by-1 matrix. Okay. And in this case would correspond to this nodal force at each of the degree of freedom. But now, because you see that we have a 2-by-2 matrix for each element, so the question is, how can we construct the equation, the stiffness equation for the structure based on the element stiffness matrix? Okay. So what we need is how to correspond the nodal displacement of the element with the nodal displacement of the structure. Okay, so you need to find this relationship then. Okay, so one of the way you can write this relationship, but is by using this what we call the connectivity matrix. Okay, so you can connect between the nodal displacement of the structure with the nodal displacement of each element. For example, for element 2, you see that the starting node and the ending nodes of element 2, right, which is this nodes right here for element 2 and this node right here. So the starting node I match with node 2 of the structure, and the ending node J match with the node 3 of the structure. So you can write something like this. Okay, to match with you have 2 and you have 3 of the structure by using this connectivity matrix. So you see that this you have I would match with you have 2 of the structure, while this you have J would match with you have 3 of the structure. So the connectivity matrix basically contains 0 and 1, right? With 1 located at the corresponding degree of freedom that match between the nodal displacement of the structure and the nodal displacement of the element. So you can write this connectivity matrix, let's call it an L matrix, right? And somehow we call it also a Boolean matrix, because a Boolean matrix essentially contains only 0 and 1. Okay, and it function is to do basic permutation. Okay, so we switch between the columns of the matrix. Okay, so you can write this connectivity matrix for each of the elements. Okay, and based on this connectivity matrix, you would be able to obtain this kind of equation. Okay, so the same connectivity matrix can also be applied for the virtual nodal displacement as well. Okay. So in the end, you can simply compute the element stiffness matrix, right? Or the contribution of the element stiffness matrix onto the structural stiffness matrix by using this connectivity matrix. Okay. So if you use this connectivity matrix, then now you can find the summation or the contribution from each element stiffness matrix directly to obtain the structural stiffness matrix. So based on this procedure, you would end up with this equation, right? Okay, so once you obtain this equation right here for this particular structure, so if you happen to know the value for the nodal force at all the degrees of freedom, okay, so meaning that if you happen to know all this P1, P2, P3 to P7, then can we solve this system of equation for U halves? Can we solve for the unknown nodal displacements if you happen to know all the nodal force components? Let me ask Parinya. Rinya, are you there? Parinya, do you understand my question? Okay, my question was, if you happen to know all the force components at each node, P1 to P7, okay, can you solve for the unknown nodal displacements based on this equation, K you have equal R? หาได้ไหมครับปริญญาถ้าสมมติว่ารู้ค่าแรงเนาะรู้ค่าแรงที่มากระทำที่แต่ละ degree of freedom ใช่ไหมคุณจะสามารถ solve equation นี้เพื่อหาค่า displacement ที่โนดออกมาได้ไหมครับได้ครับ so ปริญญา suggests that if you know this right hand side vector then you should be able to solve for u hat based on this equation but the answer is different from what Parinyas understand because if you try to solve this equation then you would find out that there would be infinite number of solutions for your u hat. Why is that? Because you would see that this matrix K would be what we call a singular matrix. Why would K become a singular matrix? Why is that? Okay, let me ask Mirin then. Mirin, why do you think K would be a singular matrix? Okay, Mirin doesn't have any answer. K would be a singular matrix because when you construct K as a 7 by 7 matrix, you did not impose any boundary condition onto your structure. No boundary condition whatsoever, right? You think of your structure as having 7 degrees of freedom without any constraints putting on the structure. So meaning that you have a bar floating in space, okay? So if you put a system of forces onto the structure, even though the system of forces is in equilibrium, even though the system of forces is in equilibrium, but because you don't put any constraints on your structure, it means that the structure can keep floating, right? Being in equilibrium because you don't have any constraint on the structure. So you allow the structure to move as a rigid body, okay, anywhere on your space. That's why this matrix K would become singular if you do not put any constraint on your structure at all, okay? And you would see that the displacement that you obtain from this system of equation would be infinite set of displacements. So there are multiple solutions to this problem. Okay. So the only way that you can prevent this kind of problem is to put proper constraints on your structure. How do we put constraint on the structure? For example, you put a fixed end onto node 1 like this, then it means that for some of these displacements, you are specifying certain values, right? For that node, okay? In this case, you're specifying a 0 displacement at node 1. Okay, but you can also specify different values. Okay. But now as you put constraint onto this system of equation, then this equation would look differently from the original one, right? Because earlier you don't know any displacement values at all. Okay. But now you specify some of the values for the displacement. So now the system of equation would be different. Okay. So how different? How different? So you would see that some parts of your equation, right? Okay. So some part of this equation would be associated with the known displacement value and some part with the unknown displacement value. So basically you can now partition your system of equation, or you can partition your matrix equation, okay, into something that looks like this. Okay. So before you want to, before you try to solve your system of equation, make sure that you impose proper boundary conditions onto your stiffness matrix or onto your system of equation. Okay. So the system of equation that we have now would become something like this, in which, okay, some part of the displacements are known and some parts are unknown. Okay. Now, where the values of displacements are known, the force components would become unknown, right? Because if you, for example, you put a fixed end onto node 1, then the force at node 1 would become your unknown reaction. Okay. And similarly, where the nodal displacements are unknown, the nodal force must be known, right? So for example, at the free nodes, right, and at the nodes that are not constrained, at those nodes, you should know the value of the applied force that act at the nodes. So you have a system of equation that look like this. So you can solve this system of equation by trying to solve them in proper order, right? Okay, so you can try to solve this equation first. Okay, this part of the partition matrix equation to obtain the unknown displacement. All right. So this part comes from this part right here. Okay. So the lower part of this equation. So this multiplied with this and this multiplied with this. Okay. Gives you the lower parts of this equation. Right? Okay. So you solve this first, and then once you obtain this unknown displacement, then you can substitute this back to solve for the unknown reaction. Okay. All right. So this looks good on paper, right? Using the connectivity matrix and then solving the system of equation by partitioning the matrix into different parts. But in reality, when you are trying to build this into a computer program, or you're trying to code this, right? Then you have to do the coding different ways from this, because otherwise you're going to be dealing with different kind of matrix. You would have to deal with a number of matrices, okay, in your computation or in your program or in your computer program. So you should be able to handle this differently from what we wrote on a paper here. Okay. So how can we do that then? First of all, how can we construct this structural stiffness matrix from the element stiffness matrix that we have without having to use this connectivity matrix. Okay. Because in a computer program, you don't want to store a matrix that contains only 0 and 1 and then do the multiplication of them, right? That's a waste of a computational resource. So you want to try to avoid that. So how do we do that without having to use the connectivity matrix? We're going to use this concept, which is similar to what you have done in structural analysis problems. Okay, in structural analysis problems, you have heard of something that we call a direct stiffness assembly, right? So we're going to use the same concept here, but the concept here is going to be called where is it? We are going to call it a is here somewhere. We are going to call it a destination vector. Okay? So what is a destination vector then? Okay. A destination vector is essentially a mapping between the element degree of freedom and the structural degree of freedom. So it's as simple as that. So it means that, for example, okay, for this element 5, if you look at the nodes of this element 5, okay, you will see that for this element 5, node 1 is right here. So you had 1 of element 5 should be right here, and you had 2 should be right here, okay? And node 2 is right here, so it means that you had 3 and you had 4 should be right here. And node 3 of element 5 is right here, so you had 5 and you had 6 of element 5 should be right here. But when it maps to the structural degree of freedom, right, or the nodal displacement of the structure, you see that you had 1 of the element maps with, you had 7 of the structure, okay? And you had 2 of the elements maps with, you had 8 of the structure. So you have this kind of mapping with 1 and 7 and 2 and 8. This is for element, this is for structure, okay? So if you write similar mapping at node 2 and node 3, you will see that you had 3 maps with 5 of the structure, and you had 4 maps with 6 of the structure, like this, okay? And you had 5 maps with 1, and you had 6 maps with 2. So 5 with 1, 6 with 2, okay? So I'm going to call this destination vector for element 5 okay. I like to blame the iPad for my bad handwriting, okay? So destination vector for element 5 becomes this information right here that is stored here. So it becomes 7, 8, 5, 6, 1, 2. So this is the destination vector for element 5. Now, how do we use this for stiffness assembly then? Because you know that degree of freedom 1 of element 5 would become degree of freedom 7 of the structure, right? So whatever is going on at degree of freedom 1 would end up at degree of freedom 7 of the structure, okay? So if you happen to have K11 for element 5, this K11, right, would end up, because 1 maps with 7, this is 1, 2, 3, 4, 5, 6, okay? Because 1 maps with 7, so K11 would end up at K77 of the structure. So meaning that the contribution from the stiffness matrix of element 5 of K11 would be at row 7 and column 7 of the structural stiffness matrix. Okay. Similarly, if you look at K12, okay, of element 5, because 1 maps with 7, 2 maps with 8, so K12 of element 5 would end up at row 7 and column 8 of the structural stiffness matrix. Okay. So instead of using the multiplication of the connectivity matrix, okay, which is a waste of time, you use this mapping of the destination vector between the element degree of freedom and the structure's degree of freedom to directly map or find the contribution of the element stiffness matrix onto the structural stiffness matrix. Okay, and this can be coded into a computer program. Okay. So in order to write this computer code, you need this information, right? So you need this mapping first. So first you need to construct the destination vector for each of your elements and use this destination vector to find the contribution of your element stiffness matrix once you compute the element stiffness matrix, right? For each element, and then you find its contribution onto the structural stiffness matrix. Okay, so meaning that you must somehow be able to construct a loop, right, for each element. Okay, so for example, if n represent the number of elements, so from 1 to the elements, then what you need to do is first you must compute Km, I'm sorry, Kn, right? Or maybe I should change this to K. All right, compute Km for element m. And then once you compute this, then you must somehow find the contribution, right, of Km into the structure stiffness matrix. Okay. Now, this should be part of your loop for each element. Okay. But in doing this, because you need to map the degree of freedom for each row and each column, okay? So it means that doing this requires 2 loops, right? One for number of rows and the other for number of columns, okay? And somehow you need to do the mapping here. Okay. And the number of row and the number of column here would correspond with the number of degree of freedom of the element. Okay. For example, if you have 6 degree of freedom for your triangular element, just as in our example, then this would become, I would run from 1 to 6, right? As well as J. Okay. So this operation would find a contribution for each row and each column of the element stiffness matrix and put it in the corresponding row and corresponding column of the structure stiffness matrix. Okay. All right. So you can think about how to code this in computer program a little more, because this is going to be your next assignment. Okay. But I'm not gonna give you your assignment for this week. Probably next week. All right. So to summarize what we have discussed, we have talked about first, we would like to subdivide our domain into a number of elements. Okay, so that's step 1. So you build a finite element mesh, and each element is interconnected with other elements at the nodes only. Okay, and at each node, the quantities at the nodes or the nodal quantities are characterized by the degree of freedom. Okay. Now, the next step, once you build your finite element mesh, what you need to compute in the end is you want to be able to solve this system of equation. Where is it? Okay, it's not in here. So you want to be able to solve this system of equation. Okay. So this is the system of equation that we would like to obtain. But in order to solve this system of equation, you need to somehow be able to assemble this structure stiffness matrix, right? Now you assemble that from the element stiffness matrix. So first, you need to be able to compute this. Okay. So the second step is we want to compute the element stiffness matrix. And again, how do we compute the element stiffness matrix? We compute this by computing this integral right here. Okay. So this is the key matrix that we want to obtain in the first place. Now, in computing the element stiffness matrix, meaning that you want to compute the B matrix, right? And the B matrix come from the derivative of the displacement interpolation matrix. So if you know this, then you can get this and you can compute this. Okay. So that's the steps that we want to follow. All right. Now, once you obtain the element stiffness matrix, then you want to assemble them, right? Assemble them into here. Okay. And the way that we assemble the structure stiffness matrix is by using the concept of the destination vectors. Now, once you obtain the structure stiffness matrix, before you want to solve this system of equation, you want to make sure that you apply proper boundary conditions onto your structure. Okay. All right. By applying proper boundary conditions, meaning that you want to somehow be able to partition your system of equation into different parts like this. Okay, like this. Then if you do this correctly, then you should be able to obtain the unknown displacements. Right? And once we obtain the unknown displacements, then you solve for the unknown displacements. Now, once you obtain the unknown nodal displacements, now you can come back to compute whatever you'd like to see within each element of the structure. Okay. For example, from the nodal displacement of the structure, you can obtain the nodal displacement of the elements and then use this to compute strain within each element, and then use the obtained strain to compute stress within each element. So from the nodal displacement of the structure, then you can do what we call the element force recovery. Okay. So you can recover any quantities of interest within your element based on the obtained nodal displacement of the structure. Okay. Or you can obtain or compute the reactions of the structure as well. Okay, if you like. Now, in solving this system of equation in computer program, as I mentioned earlier, you don't want to deal with too many number of matrices. Okay. So, for example, if you already construct a structural stiffness matrix K, you don't want to split it into K, U, K, U, like this, K, U, R. Because if you do this, then it means you have to construct 4 new matrices based on this matrix that you have. Okay, so in computer program, you don't actually partition your stiffness matrix into 4 different parts. But what you can do is you can think of having some known values of displacements and modify the stiffness equation based on these known values of displacements. Okay, so how can we modify this system of equation then? Okay, so let me maybe give you an example of, suppose we have a system of equation like this. Suppose I have K11. So this is the components of the structural stiffness matrix. Okay, so K12, K13, K14, K21, K22, K23, K24, like this. K31, K32. K41, K42, K43, and K44. All right, so I have a 4 by 4 matrix, and Suppose I have you had 1, you had 2, you had 3, and you had 4 like this, and I have had 1, I had 2, I had 3, and I had 4. Okay. So in this case, suppose this becomes a known displacement. Okay. Suppose I specify the value of the displacement for u hat 2. Okay. So this becomes a known value. Okay, so I put u hat not here as a known value. Okay. So if this is known, then one of the ways that I can modify this system of equation is, instead of split it into 4 parts, okay, I simply, okay, modify this equation by looking at this row first, the second row. Okay. Now, because this is a known quantity, so I would like to first modify this. Okay. So put the known values of displacement onto the right hand side, and then modify the stiffness matrix accordingly by changing, okay, this, 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 this to this. Okay, so if you look at the second row now, my equations would read, right, based on this system of equation. Okay, but the problem would also become the remaining equation, the remaining 3 equations, right? Because now you happen to know the value of u hat 2. So you can also modify the remaining equations as well based on the known value displacement, right? So you can also modify this, for example, I can modify this term and put this term on the right hand side. Okay, because I have a known values of u hat 2, right? So I can modify the first equation to read like this. So my first equation would read k11 times u hat 1 plus k13 times u hat 3 plus k14 times u hat 4 equals r hat 1 minus k12 times u hat 20, right? Okay. And I can also modify the remaining equation. So this would become k32 u hat 2 and minus k42 u hat. So if I modify my system of equation like this, then essentially I didn't change most of the components in here, only this row and this column here that have been changed, right? And the load vector on the right hand side that has been changed. Okay, so this is one way to do it. This is one way to do it. So you can modify, you can choose to modify the stiffness matrix itself, right? Modify its row and column that correspond with the known value of the displacement at the corresponding degree of freedom, and then also modify the right-hand side load vector accordingly. This is one way to do it. Or you can if you look at the equation here, and you want to keep this okay, as your modified stiffness. You can also solve for this system of equation as well. Right? You can also solve for this system of equation as well, without having to do much at all, right? You just choose to modify one row of your matrix, and that's it. You can try solving this system of equation, okay? And you should be able to obtain this, okay? And you could check if you get your answer correctly or not by looking at the obtained value of your U hat 2, okay? This is another way of doing it. So you can just choose, or you can modify your stiffness matrix K to what I would call K star. So K star is the one that you apply boundary conditions or the specified value of displacement onto your stiffness matrix, okay, and modify your system of equation accordingly. So there are different ways that you can choose to modify your system of equation. Now, the bad thing about this, not a bad thing, I would say a limitation to this method is that if you choose to do it this way, then your system or your structural stiffness matrix would become unsymmetric, right? So you can see here that it would certainly become unsymmetric. And if your stiffness matrix or if your system of equation becomes unsymmetric, then you can use certain what we call a solution algorithm to solve the equation. So there are efficient algorithms that you can use to solve a system of equation that you that this stiffness matrix is symmetric. Okay, so if you keep this symmetric, then you can use certain algorithm to solve for your unknown displacement. But if you choose to do it this way, then there are certain limitations to it. Okay, so that's why sometimes you would like to also modify this to be symmetric as well. Okay, so in order for you to be able to use certain algorithms to solve for the unknown displacement. So anyhow, you can do it either way, all right? But if you choose to modify your stiffness matrix to keep it to be symmetric, okay, then you can, for example, use Cholesky decomposition. So this applies only for symmetric matrix, okay? If you happen to have a an unsymmetric matrix, you would, instead of using Cholesky decomposition, you would have to use what we call an LU decomposition. So that would be a lower, it would give you a lower triangular matrix and upper triangular matrix. Okay, and it would cost you computational resource a little more compared with the Cholesky decomposition. So this difference in computational resource would be very trivial if the problem is small. But as you can imagine, if your system of equations becomes larger and larger, for example, if you're dealing with 1,000 degree of freedom or 10,000 degree of freedom, then you would expect to see this difference becomes larger. And sometimes it would mean, more hours, more days in order to run your problem, in order to solve the problem. So you have to keep in mind this kind of thing as well. So this summarizes the step involved in our finite element computation. So you can see that we start from looking at the virtual work equation as the alternative form of equilibrium equation. Okay, and by using this virtual work platform, we apply the finite element approximation scheme onto the displacement field. Okay, I would like to emphasize that we apply the approximation onto the displacement field. Okay, so with this displacement-based finite element approximation, then you can see that the steps involved is by first computing the element stiffness matrix. Okay, so once you obtain the element stiffness matrix, you do the stiffness assembly to obtain the structural stiffness matrix, and then you apply boundary conditions onto the structural stiffness matrix, and then you solve for the unknown displacements. And once you obtain the unknown displacement, you can recover all the quantities of interest for each element, and also you can compute for the support reactions. Okay. So that's pretty much it for today. So any questions regarding what we talked about today? Okay. So you can still hear me, right? I'm not sure because I can't hear anything.
Yes, อาจารย์
yes อาจารย์
Questions can be in Thai. If you don't understand any of this, you can ask me. I can try to explain to you in Thai as well. มีไหมครับ มีคำถามไหมครับที่ถามภาษาไทยได้ครับ เชิญครับ
ที่อาจารย์ว่าไอ้ที่ต้องไปทำเป็นโปรแกรมก็คือแปลง KM เป็น K structure ใช่ไหมครับ
ใช่อันนั้นเดี๋ยวจะมี assignment ให้ทำนะฮะ
ครับ
ซึ่งอันเนี้ยมันจะเป็นส่วนหนึ่งของ assignment นะครับ
ครับอ๋อ
แต่ไม่ใช่แค่อันนี้อย่างเดียวอันไอ้ข้างหลังนี้ก็ด้วยนะฮะไอ้พวกนี้ทั้งหมดก็คือจะเป็นส่วนหนึ่งของ assignment
ครับ
Okay, so if there's no question, then we'll meet again next week. Okay, so I'll see you later then.
ขอบคุณมากครับ
สวัสดีครับอาจารย์